Hello and welcome back to Differential Equations. We are going to work on 3.4, which is on mechanical vibrations. And then after the lecture, we'll talk and chat about the exam, which we pushed for the next week. So we'll figure out what to do with that. All right, let's go and see what we can learn about mechanical vibrations. So first we are going to talk about the concept, the physical concept, where you have some kind of an object attached to a spring. So we have a spring of some kind and object attached to that spring. That object will have the mass m and your spring will have a constant k, which is known as the spring constant. Now, the spring that it's not stretched is going to have what we call an equilibrium position, which is the position that the spring wants to be on to maintain minimum energy state. If you bother the spring in any way, you are increasing the energy of the spring because you are storing potential or kinetic energy, pumping the energy into it. When you let go of the spring returns back to its original length, and in that case the spring is, we say the spring is in equilibrium. So we will call this position here the equilibrium position. So, lowest energy state. And the force for the spring is computed using the Hooke's law, right? Which is the Hooke's law, which is the law that connects the amount you need to compress the spring with the force that you need to use to compress the spring. Remember that the two springs can be the same length, but then they might have a vastly different spring constant, which means that one spring would be way stiffer than the other. Say you think about the spring that is in the shocks of your car and the spring that is in a pen. So we can technically make them to be the same length, but one holding the car will have a way larger spring constant, and it will be way harder to compress than the one in a pen, which you are supposed to just, click easily with your thumb and turn the pen on or off. So the K is known as the spring constant. And technically that's the one that decides how stiff the spring is. So that's the one that describes the stiffness of the spring. So we are going to now take a look at another constant which we have in these systems, and that constant is going to be called the damping constant, because we can also introduce some kind of a cylinder which will make the spring behave a little bit differently. So you can attach some kind of a cylinder over here of some kind. Let's put the the piston in there. This is connected to the piston, and we'll put some kind of a liquid in the back. So if you have this kind of a system, then it will be harder for the spring to restore its original length, which means to go back to the... it will eventually get there, but it will have a delay. So in this case, right, which if we introduce what is called the dashpot, that will introduce, so the dashpot here, let's go, introduces damping constant. C. And this damping constant is going to make it a little bit harder. It will introduce the delay for the spring to go back to equilibrium position. Now I'm going to also talk about the damping constant in a different light. This is an experiment that you guys can do after the lecture. Hang off of the ceiling, mass M, then bring it back to a side and let it go. It will start swinging left and right. Wait, I don't know, whatever amount of time, and if you have a chandelier in the house, you are already set for this experiment. Just don't get slain by your parents, all right? So you can swing this, right, the bob, left and right, and it will eventually stop. Why does it stop? It stops because of the damping constant C. In this case, gravity and air resistance together are the ones that will stop this from oscillating. Now, if you go in space, far away from celestial bodies like stars and planets and so on, and you are in a vacuum, right? So you are in a vacuum, far away from gravitational pool of whole bunch of celestial bodies. In this particular thought experiment, you are in between two galaxies, let's say. Between two galaxies, you are far away from any galaxy. If you do this experiment in space, in those conditions, it will never stop oscillating. It will just be going forever. So this will stop because of air resistance and gravity. And those two together, right, air resistance and gravity, will be C, which is the damping constant. We will be repeating pretty much this lecture later on in a chapter for electrical circuits, so we'll have something very similar there. Cool. And there is obviously an external force which makes all of this go. You either need to punch or pull on these objects in order to move the spring out of the equilibrium point. So therefore, we are introducing also the force, which is mass times acceleration, which is mass times the second derivative of the position in time, which would give us our second order term. Now, mass is just a number, which is constant no matter which planet you're on. We have our constant coefficient second order, as you can see. So now we are going to set up the equation for mechanical vibration here, and we are going to call it mx double prime plus cx prime plus kx equal to 0, which is equation that we can use for the horizontal, right, motion, because we are using x to measure distance, which is left and right. We can also use my double prime plus cy prime plus ky equals 0 for vertical. Now, observe that both of these are equal to 0, which means no external driving force. And actually, that is what we are learning in this lecture. What's going to happen in the next lecture, I believe, is 3.5. Just quickly check. Yep, 3.5. We are going to start introducing driving function on this side. So there will be some kind of f of t, right? All of this happens in time. So our variable, our independent variable for both of these problems here is t. Both of these have a t. So it is x as a function of t and y as a function of t, because the position of the object m, right, with mass m, depends on time. This made me think of what Joker said in Batman. Depending on time, yeah, what is it? Harvey Dent could be in one place or several. So the same thing happens here, right? We have the position of the object is dependent on time. So whether it's a horizontal or vertical positioning of the object. So we are going to have later on in later sections a function here which would be adding energy into the system, right, to interact with the system. So right now we are observing a system that it's not impacted by external forces. There will be no extra energy added to the system. The system is set in motion and just left to its own devices. Now, both of these equations here are constant coefficient, right? Constant coefficient, linear, second order, homogeneous, because it's equal to 0, right? So constant coefficients, I'm just going to say MCK, linear second order because we have x double prime, and homogeneous because it's equal to 0. So these are all of the words, right, terminology that we learned before that are important. Cool. So now we can also take a look at some of the cases. So what's important for us to know here is that if c equals to 0, motion is called undamped. I'm going to explain what this means. Give me 1 second. And if c is larger than 0, motion is damped. So, what is this? Remember what I talked about earlier, that you can have these two different situations when one is just an object connected to the spring and the other one has the dashpot? Well, that's the difference between the two. See, damping constant C appears for the second part. It is not in the first. So the top situation has C equals 0, and the bottom situation has C larger than 0. The same thing happens with our pendulum, whether it's in space or it's in your living room, right? If in space C is equal to 0, the pendulum will be swinging forever. Where in your so now, when we look at this equation, we have 3 constants. Mass, you do not get to change the mass of the object that it's attached to the spring or to the string for the pendulum. So both of these are oscillation motion. Again, C is the damping constant. In case of the pendulum, that would be the air resistance, it would be gravity, and that is constant from place to place. And then finally you have the constant K, which in case of the spring, right, constant K is again a constant because it's the one same spring that you have. It doesn't change over time, right? So MCK are all constants, and you now either have horizontal or vertical problem depending on situation you have, but it's at the same time it is the whole, right? It is the same problem. So now what we are going to do is we are going to say that we have the equation. Let's first deal with the undamped, so free undamped motion. So this is our now subtitle. The word free means homogeneous. And that was our equal to 0 part. And undamped means C equals 0, right? So what is our equation? Our equation that we are observing is going to be mx double prime plus kx equals to 0. So this is the second order linear ordinary differential equation which is homogeneous, and it has constant coefficients. It has lowercase m, which is a mass, right, and k, which is a spring constant. So maybe we should add that also over here. So m is the mass and k is the spring constant. So we are going to take a look now at the situation where we have are going to define, and we'll see why. Right now we're just defining this, omega naught, which omega 0 or whatever you want to call it, as k over m. Now, why would you do? Actually, you know what? Let's do it this way. Hold on. Divide the entire equation by m to get x double prime plus k over m x equals 0. So this is our situation. And now I don't like this fraction here, so I want to get rid of it. But I also know that what's coming up in the future is my, you remember, r squared problem? So it would be nice if this was factorable, which is why we are going to define omega 0, omega naught, to be square root of k over m. Now from there, k over m will be omega 0 squared, which would give us an equation x double prime plus omega 0 squared x equals to 0. Now we'll explain omega later. Right now we just want to focus on solving the equation. So we still don't know what this means, right? In terms of physics, in terms of reality. Let's just deal with math first, and then we're just going to explain it in terms of reality. So we are only over here, what we are doing now is mathematical manipulation to make our life easy, because characteristic equation for this is r squared is r squared plus omega 0 squared equals 0. So that's the characteristic equation to solve. Remember, that was the thing we learned in the previous class with the homogeneous equations, when we said that, well, let's go all the way up somewhere over here, right? When you have constant coefficient, we write characteristic equation and we keep all of the same coefficients, right? Well, in this case, we don't have the middle term, right, which was x prime. We don't have x prime because the damping constant c was 0, right? So we'll just get rid of that, and we had our equation. All right. So here is our equation, and what happens here is this factors over complex numbers, right? Because your r squared will be negative omega 0 squared. This is not w, this is omega, Greek letter omega. Omega has capital omega, which is used for ohms, and lowercase omega. So those are the Greek letters, right? So what we do is take square root of both sides. When you square root both sides, you have to put plus minus in front, right? And you are going to get r equals plus minus I omega 0, right? And this is why we defined it to be squared. See, so this square root can kill that square, and we just have omega 0, so we are not dragging square root of omega throughout the problem. We are just going to have it as omega 0. And now the solution that we are used to is x of t equals, look, there is no real part, so we are not going to have the e portion of our solution. Remember that the solution was e to the at plus sine and cosine, right? Well, if your a is 0, then it becomes 0 times t is 0, e to the 0 is 1. So you just have sine and cosine part. So it becomes a cosine omega 0 t plus b sine omega 0 t. Now, some of you that are a little bit better in physics are already recognizing the solution, and you're already seeing what's happening here. And you're probably going, oh, that's why the formula for so-and-so is so-and-so, right? Anyway, so we have this, and now we have our solution for this equation. This over here is known as angular velocity. That's what it is. Now, it's also known as circular frequency. And it is connected to the period of oscillation. So all of these things are all connected, and they are all on a pile. So what we are going to do here is now we're going to understand a little bit of what these constants and variables are. So to analyze this a little bit, we can either, well, first of all, there is a way to combine this answer into another answer in terms of a cosine only. It's a mathematical manipulation, and sometimes our solutions are represented in terms of that one, and then it introduces the phase shift in our answer. What you have in the original answer here are two trig functions, right? We have two trig functions here, and the answer is the superposition, right? The sum, superposition, the sum of the two trig functions. So if you have one function to be some kind of a sine function, the other one is some kind of a cosine function, right? We need to add these two, and you add them simply by just adding up y values, right? So you have This value plus this value is that value. This value doubled is going to be here. 0 plus this value is this value. 0 plus this value is this value. This value plus this value is here. This value plus this value is that one. This value plus this value is that one. So now you can see that I can draw another graph, right? So you can see that I can add, and if I can do it graphically, I better be able to do, well, not better be, but I might be able to add them also algebraically. So I can add two graphs together, right? They're going to have different amplitudes. Amplitude A and B is how high the graph goes. So if you recall your tree course, you have your A equal 1, and then you have your A equal 2, and your A equal 3, right? So it is literally times 1, times 2, times 3, times whatever. It could be 0.7, but whatever it is. So we get to add physical heights, the y values. We get to add them and then combine this into a single problem. So now let's actually first do that conversion before we move on. So to analyze the solution, to analyze the motion, we can draw the triangle, right? We will, okay, let's call this angle alpha. I would like I like phi better than alpha, but such is life. ABC, you have your two amplitudes here, and we can write our sine alpha as B over C and cosine alpha as A over C. So hey, this is great. If I just take my formula and divide and multiply by C, okay, that sounds good. So x of t is equal to C times A over C cosine omega 0 t plus B over C cosine omega 0 t. What I did is I divided and multiplied by C. Well, that was C over C, right, which is 1, so no harm done. But now when you look at these two, you see that you can replace them into the problem. And the A over C is cosine alpha times cosine omega 0 t, plus B over C is sine alpha cosine omega 0 t. And do you remember the cosine of the difference formula from pre-calc? Maybe not, right? Cosine of x minus y was cosine x cosine y plus sine x sine y. Hey, we have this. We have that. So condense it now. So x of t is equal to c cosine of omega 0 t minus alpha. You probably have seen this in physics as a cosine omega 0 t minus phi, right? That's probably how you've seen it in physics, because we generally use phi, or maybe, depending on which professor and who teaches it, right? Use psi or something, but whatever. Or theta. I don't know. It depends on the notation. But that's that formula. I mean, it's the same formula, always the same formula. So now our solution looks like this. Our C, clearly, from the formula up there, because it's a triangle. C is equal to square root of a squared plus b squared, right? Because those are your a and b. So when you solve the problem using constant coefficients, you are going to get maybe 3i or whatever. You use your initial conditions to calculate a and b, and then you can square a and b, add them, and take the square root to calculate c, and just figure out what alpha is later. All right, so now what we have here is C is the amplitude. I'll put in a parenthesis, let's use purple, I guess, so it can stand out a little bit. How far it goes. What do I mean it? Well, if you have a pendulum, how far out it goes. If you have a spring, how far out it goes to left and right, and so on. You can also have a spring suspended on the ceiling, right? So how high, up and down, right? That's that. C. So now we also have omega 0, which is called circular frequency. I also called it angular velocity for if you have pendulum like swinging left and right, or how fast is it moving. Now I will still put in parenthesis connected to period. It's very important to understand oscillation and the period, right? The connection between the frequency and the period. You ask yourself, how frequently do you go to the store? Well, actually, now you don't go to the store. How frequently you eat during the day, or whatever, right? So that's how frequently, right? And the more you do it, the shorter the period of time before you do it again, right? Right now in this situation, when we're all stuck in our houses, what do? You eat like 17 times a day, right? Stress eating or boredom, whatever, right? Because you're eating more frequently, there is less time in between two meals. That is called periodically, right? Periodically. So period and frequency are measuring the same thing in opposite ways. The higher the frequency, the smaller the period. If you eat more frequently, the time between meals is less. If you eat less frequently, the period between two meals, right, the time between two meals is more. So you have more on one, you must have the less of the other, because they are connected through the formula of period is 2 pi over omega 0. We'll get there. Well, actually, I can write it here. Period t is 2 pi over omega 0. That's what it is. Finally, the last one on the list is alpha, which is the phase angle. And this is what it's known as. All of this over here, how about that? All of this is called simple harmonic motion. Go ahead and figure what the complicated harmonic motion looks like if this is simple. Now, phase angle, phase shift, what is that all about, right? What does that mean? Well, that will introduce some time lag. If you are a gamer, you know that for first-person shooters, you need a good reaction time. What is the reaction time? You can measure it on. You can go on the website that measures reaction time online. You have to be clicking the mouse, obviously. The screen will appear red, and then when it flashes green, you click as fast as you can, and you can measure your reaction time. So what you are technically measuring is the time lag, which is the phase shift, connected to the phase shift. You are measuring the time lag between you seeing something and then reacting to it. So professional gamers need to have that less than 160 milliseconds if they are to compete. I mean, you can't have time higher than, forget it. If you have more than 200, there is no way that you can be serious competitive or anything. I mean, 200 is actually a lot. So yeah, you can go and measure that yourself. What else is a time lag? Mars lander needs to be fully automated, needs to be moving very slowly on the surface of the Mars, because it takes a long time for a signal to travel back to Earth. On average, could be even 8 minutes for a signal to travel one way. So when the Mars rover sees something through the camera, that signal is transmitted to Earth, is going to be on Earth 8 minutes later. Then on Earth, if someone is driving it like a drone, right, with the joystick from Earth, then the person will say, "Oh no, turn left," right? The person turns left. That turn left signal will travel back to the rover another 8 minutes. So that's what the time lag is. You have a time period in which there is no communication possible, right? No communication possible. And that's all connected to the phase angle. So I gave you 2 examples of what the phase angle is and how it produces the time lag. So things never happen instantly. The life on this planet would not exist without the sun. If the sun is to be removed from the picture completely, let's just disappears, nothing would happen to the planet Earth for 8 minutes. Nothing. Now, why did I say Mars 8 minutes? Because on average, remember that we can be on 2 opposite sides of the sun. If it takes light 8 minutes between us and the sun, then between us and the Mars, if it's on the opposite sides, could take 16 minutes. But then Mars could also be lined up closer to the Earth. So on average, it takes 8 minutes. But it depends really where could take 11 or 10 or whatever amount of minutes between, let's say, 1 and 16, right? So if the sun is to disappear, gravitational pull of Earth would not get out of its orbit around the sun for 8 minutes. That's the time lag right there. Because all information, including gravitational field, right, information, travels at the speed of light. So the time lag is there. All right, cool. So let's see. I already gave you the formula for angular circular frequency. Okay, so here is the formula for frequency. And the frequency, nu, that's not a V. This is V. This is nu, which is curved V. Greek letter. Yeah, you gotta stop eventually and learn the Greek alphabet so you can survive in your STEM courses later on. It's going to be a really 1 hour well spent to learn all of the letters, and so you're not freaking out when you see C and stuff like that moving on to your 4-year school. So yeah, do that. You have seen mu, you have seen a whole bunch of stuff, but rho and theta, and just learn them all. All right, so frequency is going to be 1 over period, which is clearly angular velocity over 2 pi. I think I have all of the formulas. Let me just see in the book if I missed any of the stuff. Oh, time lag. Okay, this is the last one. I don't want to make a big deal out of time. Let's put it also purple. Time lag. So for time lag, they're using delta, another Greek letter, right, which is equivalent to our D. You have a capital delta, which is that triangle thingy like that, and lowercase delta looks like that. Delta is equal to alpha divided by omega 0. Ooh, one thing that I have to write in blood over here, otherwise you will be doomed. All angles must be in. Please complete this sentence for me in the chat. I'll wait. What is the word that goes here? Please complete this in chat. I'll wait. Very good, guys. Yes, all of you are getting it correctly. Radiance, radiance, radiance. Yes, radiance. You have to filter the degrees. Degrees are good for a measurement, and that's it. All of the calculations have to happen in radians, because radians are what is the ratio between the arc length and the radius. Degrees are a part of a whole. So you can think of a degree as like a percentual measure. It's not a percentual measure, but what you can do, instead of dividing, well, it is in some case percent, but it's not percent, it's over 360. So you take a circle, and instead of dividing it into 100 pieces for 100%, you're dividing it into 360 pieces for 360 degrees. So it is literally working the same way as a percentual measurement. That's what the degrees are. Very useful for engineering to simply say, yeah, 43.7 degrees and so on. Very easy. But for mathematical calculations, for formulas, you can never use degrees. You also know that if you try and graph something in your calculator and you leave your calculator in degrees mode, you don't get to see the graph because, the scale is not done properly. So all of the graphing in mathematics is done in radians. All of the formulas that contain angles in mathematics are all done in radians. Now, you can still write sine of 15 degrees. It's okay. But if you see a theta or omega or alpha, something in mathematics, the default is radians. So please, 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 not just for this class, for any math class, always radians. And that's it. So now let's take a look at example. Now, obviously, 100% of problems here are going to be word problems because we have a section that it's applied. So we're going to have pendulums and we're going to have all of these guys. Now, guys, this is only the first case when C is equal to 0, right? We still have the second one when C is not 0, right? So this is a non-damped case called simple harmonic motion, meaning you swing the pendulum and it's just gonna go forever, left and right, left and right, left and right. I wonder if this, let me just check how well are we doing. Yeah, we're doing over 2K on the stream over there, so I'm feeling the lag on the tablet as well, and it's just 11 a.m. is a bad time for bandwidth on YouTube. Apparently, I did not have issues streaming any other classes other than 11 a.m. I am able to do 1 o'clock, 3 o'clock, 5, 6 p.m. All of them worked great. Just 11, I guess, because everyone is working from home and YouTube can catch up, I guess. I don't know. All right, so let's take a look at a quick example and see all of the cool things we can calculate. So a body mass of 0.5 kilogram. So mass equals 0.5 kg. Is attached to the end of the spring stretched 2 meters by force of 100 newtons. So spring stretch 2 meters with 100 newtons. Is set in motion with initial position x0 equals 1 meter and initial velocity v0 equals -5 meters per second. So we'll have to deal with that. We'll obviously draw a picture and try and see what is going on. So what do we have? Find the function as displayed. Find the function of the body as well. The amplitude, frequency, period oscillation, lag, blah, blah, blah. Okay. So this is what we have. Is stream looks like it's on. I don't know. This looks frozen to me, but let's see if it works. What do we have? We have spring constant, stretch 2 meters with 100 newtons. I have to calculate K. F equals Kx, force of 100 newtons, K, stretch 2 meters, K equals 50 Newton meters. Newton per meter. So this is what we have. And then we have our mass of kilograms, so we can write our equation of mx double prime plus kx equals 0. M is 1/2 x double prime plus 50x equals 0. We multiply everything by 2 to get our differential equation